pressure is probably how you're feeling about your exams right about now, but let's have a look at what it means in physics. So pressure is defined as the force per unit area. There's an equation for it, but you need to know the words as well. Force per unit area, meaning that if I was to divide the force by the area, I would find the pressure. Now this is really useful for paper 2, but also for paper 1, talking about gas particles exerting pressure on a bike, tire, or something, any sort of surface. When the gas particles collide with the container wall, they exert a force, which means there's pressure. So it's useful for both papers, this. Now the units, force is in newtons, area is in meters squared, so therefore pressure is in newtons per meter squared, also known as pascals. Both units are absolutely valid. Now, let's have a look at what this means then. I've got a shoe up here standing on some ice. If I were to increase the area, the pressure would go down, meaning they're inversely proportional. Now, that is useful in a couple of different situations. Let's say you are trying to not sink through the snow. Snowshoes have a bigger area, so exert less pressure. Camels have already evolved to make use of this by having large areaed feet so they don't sink through the sand. Let's look at the opposite. What if I were to have a lower area? Well, in that case, the pressure would increase. That's useful in situations where you want to go through a surface, like, for example, the blade of a knife, or drawing pins, or football studs. Whatever you're designing to go through a surface, having a lower area makes the pressure increased. Now, the other thing that also could affect pressure is force. If you're going to have a higher weight, for example, going through the ice, you're going to have a higher pressure, so more likely to go through. Those things are directly proportional to each other. Now, as well as having pressure on surfaces, so usually solids in this case, that's where the force have got to exert on an area, you could also have pressure in liquids. So let's look at how that would work. I've got a container below which is filled with water, and it's got to have 3 spouts in even intervals up the side which water can come out. Now, assuming they're identical, which one is the water going to come rushing out of the quickest? So you might be able to figure out the water is going to come the furthest out of the bottom spout. So why is that? Now, at the bottom, it has the biggest amount of water, the largest volume of water above it, which is going to be really important to explaining why the water comes rushing out fastest there. So at the bottom, we say the pressure is greatest. Now, the reason the pressure is greatest is because there is the greatest weight, or is due to the weight of water above that point. Now, we should remember that weight of water, weight is a force, and that's in our equation. So that's our little hint there. Weight is a force, so therefore bigger weight, bigger force means a bigger pressure on that point. Now, there is an equation to calculate pressure in a liquid, and it looks something like this. It depends on the height below the water's surface. It also depends on 2 things you've come across in paper 1 as well. Those 2 things are density, given by the symbol rho, like a curly P, height, as we mentioned, and G, which stands for gravitational field strength. Now, let's look at units. The easy one to know is that height, as always, distance in physics is always with meters. Gravitational field strength is in newtons per kilogram. Now, on planet Earth, they'll always tell you this, but it is a roughly 9.8 newtons per kilogram. It would be different on different planets. And density has to be in kilograms per meter cubed for this to work. So it's quite a difficult equation, but if you know how to put your numbers in and rearrange, it's just the same as any other equation to work out pressure. Now, pressure we can also find in the atmosphere above Earth, so it's called atmospheric pressure. Now, atmospheric pressure is actually way, way higher than you might expect. So it's caused by the air above the Earth, just a layer of air above the Earth, which we call the atmosphere. And now that air, even though it doesn't seem like it, air does have a weight, it does have a mass. Okay, and now if you were to add up all that mass acting on 1 meter squared, is actually really high. It's 100,000 pascals, or 100,000 newtons per meter squared, which is equivalent to something like 17 elephants or weighing on top of you right now. Now, atmospheric pressure isn't constant, okay? So as you go higher, so a greater altitude off the surface, the atmospheric pressure decreases as the altitude or height increases. The graph for it would look something a little bit like this. So if you were to have altitude on our x-axis and pressure on our y-axis, it would have a kind of curved shape a little bit like that. Now, the reason the pressure decreases is really important. The pressure decreases because there's less air essentially. Air has a lower density at higher altitudes. Now, at higher altitudes, the reason it has a lower density is because air has a mass and gravity attracts it towards the surface of the Earth, meaning there's less of it the higher up you go. Now, to calculate it, we can use this equation from before. Air has a density, G is still G, gravitational field strength, and height would be the height above the surface of the Earth. Now, the last thing we can explain with pressure is upthrust. So upthrust being if you have an object submerged or on the surface of water, it'll have forces acting on it. Downwards will be weight or gravity, upwards will be upthrust. So how does pressure help us explain that? We looked at earlier, at the bottom of our container there is higher pressure and at the top there is lower pressure. Now if there's higher pressure near the bottom, we learned earlier that pressure is proportional to force. So that means there's going to be a higher force at the bottom than there is at the top exerted on the object. There's also going to be forces from the side as well, but they're not relevant to talk about upthrust. So what we'd say is that the higher pressure leads to a larger force below the object than above it. And that's due to, like I said, the pressure being proportional to force. That leads to an upthrust pushing the object upwards and balancing weight if it's going to float.